Hey guys, welcome back. We're going to be solving another question from the third chapter of the engineering mechanics by Meriam. And in this one, we need to determine the moment M, which the motor must exert in order to position the uniform slender bar with the mass of M. So we're talking about this bar and the length of L in the arbitrary position theta. So it has to make this angle theta with vertical, and we know also the ratio of the radius of the gear will be attached to the bar to wheel A is 2. So what happens in here is that the wheel A is gonna turn in this direction counterclockwise, so it makes the wheel B turn in this direction, so it's gonna hold the rod in the bar in this position, which makes angle theta. And obviously we are in equilibrium, so we can use our equilibrium equations. But before that, we're going to start with the free body diagram of each of these. So let's start with the free body diagram of the wheel B and the rod that is attached to that. So we're looking for the angle theta in here, and obviously we're going to have the weight of this slender bar. We know the mass is M, so the weight would be mass times acceleration of gravity. The other forces, so we have a pin at point B, which means we're gonna have both x and y component, by, just show our x and y in here, and the gear A is gonna exert the force perpendicular to the radius in here, which we can call it F, and that's our first free body diagram. And in here, if we just do sum of all moments about point B counterclockwise positive, since we are in equilibrium, this will be equal to 0. We're gonna have the moment of the F, and for now we can consider the radius of the wheel AR, and since we know that the radius of B over A is 2, so we're just gonna consider RAR, so the radius of wheel B would be 2R. So here we're gonna have the moment of the F. So since it's counterclockwise, it will be positive F, and the distance would be the radius of the wheel B, which is 2R. And we're gonna have the moment of the weight of the slender bar, which is gonna be a clockwise moment, so negative. mg would be the force, and we are looking for the vertical distance from B to the line of action, which is basically this distance. And if we look at this right triangle, this angle is also theta, and since the slender bar is homogeneous, so we're gonna have half of the center of mass would be exactly at the center, so we're gonna have L divided by 2 for the hypotenuse of that right triangle that I'm highlighting in green. So if you want to find this distance, we simply have 1/2 of L sine of theta. So mg times L divided by 2 times sine of theta equals 0. And here our F would be, if we just divide everything by 2R, will be mgl 4R sine of theta. So that's what we get from the first free body diagram. Let's do the free body diagram of wheel A, or the gear wheel A. And based on the Newton's law, let's just draw this a little bit smaller. Based on the Newton's law, we're going to have the same force F in the opposite direction. So that would be our F. And since we have a pin, we're going to have AX and AY, but we don't need to find those. And we have to consider one moment in here, which is the moment that the question is asking. We need to determine the moment M, which motor has to exert. So we're going to do the same thing. We have our equilibrium equation. This time we're going to do the moment about point M. So basically we're going to have the moment of the force F in here, which as we can see will be in this direction. So counterclockwise it will be F. The radius of this gear wheel is R. That's what we call RAR. And we're going to have the clockwise moment that we considered equals 0. So our M is basically F times R. We found F in the previous part, so mgl divided by 4R sine of theta times R, so the R would be cancelled out, and the moment would be quarter of mgl sine of theta, and the moment is clockwise. So yeah, that's the final answer for this question. Hope everything was clear. Let me know if you guys have any questions, and you guys take care. I'll see you in the next video. Have a good one.